Hey, morning. We are at Mayberry State Park this morning. It's getting really hard to see the birds in the trees with all the leaves coming in, but we're looking for an eastern meadowlark this morning. This is the meadow at Mayberry State Park. A lot of meadowlarks spotted here yesterday. If you listen really carefully, there's this thing that goes wheat, wheat, wheat out there. Hear it? Right there. I'm gonna try to get a picture for you. Hey everyone, we are on Gottfredson Road in Superior Township. There's horned larks around here. We saw some last night, but I didn't get a good picture. And so we're gonna go walk up and down the road and see if we can find some in the fields. There's also sparrows and a bird called a dickcissel. So we're gonna walk around and see if we can get some pictures for you. So come on, let's go try to find a bird. Horned lark. It's in the field out there. We're gonna try to get a picture for you. They're really hard to see. They have a yellow and black face, but they're all camouflage on back. So I'm gonna try to get a picture for you. Wish me luck. All right, everyone. Welcome back. I hope you enjoyed all the birding. I love the birding. I don't know, maybe you get some entertainment out of it at least, watching me run around. Also, I got a haircut, so my hair is trimmed now. And I want to circle back now to some chemistry. We just kind of want to wrap things up. And looking at the last couple reactions we did, the baking soda one and this making of a solid one. Circling back now to the burning one. So this is burning methane. And I want to kind of look at what's happening, how many molecules of each thing we have, and why does that, how does this show conservation of matter or mass? It's some of you asked, is the conservation of matter or mass the same or different? It's the same thing. But now we're thinking about what's happening to the atoms here. So I have methane, remember. Methane is here. Methane is the gas. Oxygen is in the air. And I need something to get it started. So I need energy. That's what the clicking is. It's a spark. So you get a spark to get the reaction going. And then when you have it burning, so if I just have methane going on, nothing happens. But if I get the reaction going, I start burning, and it starts making stuff. And so here, let me turn the stove on. Okay, so I'm gonna turn it off real quick. You can see here, I have some fog. That's water vapor. Okay, so a lot of you point out that is water vapor. I make water when I burn stuff. And I also make carbon dioxide. And we know that because we did the experiment and we had bromethymol blue, the blue stuff that turned yellow. That is an indicator that tells us that we made carbon dioxide. So let's take a look at this reaction and see what the atoms are doing. All right, so we are going to take a look at a chemical reaction here. And what I'm going to do is we have this reaction, burning of methane. We're going to start with that. And just like last time, we're going to start with the bubble. So I want to make sure we think about atoms. The atoms are the individual things. So there's one C atom, there's 4 H atoms, and the whole thing is a molecule, or call it a bubble. And so if I have one of each thing, like this here, and we can do the same thing. I have C's, H's, and O's on the right side. So you're going to take this just like we did last time. We have a C here. We're going to move a C up in here, move some O's up in here to show me what is going to be in these bubbles. If I have one of each thing, how many C's, H's, and O's are going to be in this reaction? Okay, so if I look and see, well, the left side of the arrow, make sure you look at this giant thing here. Left side of the arrow, there's one C. H's, count up the H's, type those in. So type those in here. Do the same thing to the right side once you have that filled in. And then why can't this reaction happen the way it's set up? Why? I mean, we had this thing called conservation of mass or conservation of matter. Why doesn't this support the conservation of matter law? And so, to help us figure out how this can happen, because we know burning stuff happens. We can burn stuff. It supports conservation of matter somehow. We have to be able to change the numbers of these things. And so to do this, what we're going to do is we're actually going to go to a simulation. I like drawing things, but the simulation seems to work pretty well. And we're just going to do it this way. So this is what it's going to look like. And so I'm going to show you, so if I go to this screen here, this is a simulation. You click on this, we initially click on this, and we're going to go to combust methane. So do that first, like that. Up here, make sure that you change this, okay? So we're going to change this to tools and use the this button right here. And then that's going to give me kind of an atom count. I'm going to just be able to see how many atoms I have of everything. Then go ahead and just, we're going to change it to one of each. So I have one CH4, so that's CH4 right here. One of the oxygens, O2, one CO2, and one H2O. So hopefully when you did your previous thing, you got these numbers. And what we're going to do now is we're going to, I know people want to just play around with it and change things until it's all balanced and get the happy face, but try to think it through and see, well, what am I going to try to, what am I going to try to balance here? So let's take a look and see. Carbon, okay. Carbon right here, I can't draw, I don't know why. So carbon has one C and one C. So I've got one carbon on both sides. That, if I start with one carbon, I have to end with one carbon. So right now, this is actually okay. This is a balanced element or balanced atom. But let's look at hydrogen, okay? Or so hydrogen, I have 4 of them over here, but I only have 2 of them over here. And so I need to have more hydrogen on the right side because I can't start with 4 and end up with 2. That's destroying matter. So I need to change that, okay? So I'm going to change the numbers of hydrogen over here, but I can't just add hydrogen by itself. I have to add it as H2O. I have to change the numbers of things that I'm making. So what am I doing here? Well, I'm making H2O that has hydrogen in it. So I'm going to change the H2O. I'm going to change that. Well, what happened? I added an H2O, so I now have 4 H's. I have 4 H's here. But in doing that, I also added an O. Okay, so I added H2O, but it's got an O there. So what does that mean? Well, I have 2 O's on the left. I have 4 O's on the right. I need to make sure that I have equal numbers of O's on both sides because I can't start with 2 O's and then all of a sudden have 4 O's. That's making matter. I can't do that, right? So I can't have more than I start. I can't have more at the end than when I start with. So how do I get more O's on this side here? Well, I got to take this and say, well, there's no O's in this thing here, but there are O's in O2. So I can add some O's like this. And if I add this, now, ta-da, I have equal numbers of stuff on both sides. So thinking about a couple different reactions, you're going to do this. I'm going to have you kind of, once you have that, these numbers here, these are called coefficients. That tells me how many of each thing I have. So I have 1 CH4, I have 2 O2s, I have 1 CO2, and I have 2 H2Os. That, you're going to put those numbers in here, so the coefficients in here, and then do a final count. Show me that you got the correct numbers for the atoms here. And then, just kind of in your own words, why explain why we can't have just one molecule of each thing to do this reaction, or why I can't stop midway in the balancing. Why doesn't that show a completely balanced equation? Why doesn't that show the conservation of mass? Okay, you're going to do the same thing for a couple other reactions. So the other reaction is going to be ammonia, this one here. N2 plus H2 goes to NH3. That is this one right here. So you do the same thing. You're going to have this molecule N2 and H2, NH3, do the same. Make sure this thing up here is set. And then the last reaction, we can actually do, I'm not going to mess around with ammonia. Ammonia is toxic. It's not good for you to breathe. But water, we can actually do this reaction. So I'm going to stop for a second. I'm going to show you the experiment, and then we'll come back and take a look at what this reaction looks like. Okay, so this last reaction we can actually try at home. It is the taking of water and everything. I can't really do a whole lot at home in terms of chemistry reactions, but I can take water and we can actually split water. So we know that water, if you heat it up or cool it down, you can make it into ice if you cool it down, which is just, remember, that is just solid water. It's still water. But now the attractions are taking over and it's this solid water. Or I can boil water, so I'm breaking the attractions, but it's still water because water is boiling up. I can put my hand over it and it gets wet. So that's still water. Now, what I want to do is actually take water. Water is hydrogen and oxygen bonded together. And I'm going to take the water molecule and break it apart, okay? So actually, let me get my model kit and I'll show you. So I still have my water molecule from I have this. This is my water molecule. Well, it's already breaking apart. I don't want it to break apart yet, but this is water. Okay, so water is a molecule. It is held together by bonds. And in the water molecule, if I have more than, okay, that's poor planning, but if I have more than one water molecule, let's say I have 2 water molecules, these are held together as a liquid by attraction. So water is still water. If I had this cup of water right here, it is millions and billions of water molecules all held together, but the water is held together by bonds, but the water molecules are attracted to each other by attractions. So these they're all sticking together because they are all millions and billions of these are clumped together so I can see them. Okay, what I'm going to do now is instead of just, if I boil water, the water just stays water, but it just goes away. I have this water here, and we boiled it like first semester, and the water just starts evaporating, breaking away like the attractions, but it stays a water molecule. What I want to do now is I want to take this molecule and actually break it apart and do a chemical reaction with it. I want to make hydrogen by itself. So hydrogen is actually H2. There's two atoms of hydrogen, and I want to make oxygen by itself. Okay, so the way that you do this, the way that you break water apart is you need electricity. So what we're going to do is something called electrolysis. If you take like a glass of water like this, water itself actually does not conduct electricity by itself. Believe it or not, it doesn't. If it's pure water, it won't conduct electricity very well or at all if you don't have any sort of things floating around in it. We need something called ions in it. So I'm just going to take some salt. So this is just table salt, okay? I'm going to put some salt in here. And put a decent amount in. You don't want to, you want to make it so that you have enough in there so that you have enough ions to get it to float around. I'm going to stir it up to get it all dissolved. You need a battery. Bigger battery is better. If you have a 9-volt battery, that works great. All I have here is just a AA battery. And so that's all I'm going to use. And you need some aluminum foil. So I'm going to take some foil. what you're going to do is take the foil and tear it off a strip, fold it up so that it is, you know, it's not too wide, and you're going to use this kind of like a wire, and you're going to need 2 of these. I'm going to take this, and you're going to hold one end here and one end here. Okay, what you've now created is basically a set of wires that you're going to use to conduct electricity, and electricity is going to conduct through here. So now we're going to take this, and let me see if I can do this. I'll try to set this up, and I'm going to put this in the water, and I want you to look at the aluminum foil to see what forms on the foil. So here we go, really close. Don't stick the aluminum together. So I don't know if you can see that at all, but on this side here, can you see the bubbles forming? There are bubbles forming on the electrode or the aluminum. There's actually more bubbles forming on one of them than the other. And that's because one of them is hydrogen. You're actually making hydrogen gas. The other one is oxygen. We're making oxygen gas. And this is getting hot now, so I'm going to take this off. Whew. So we made hydrogen, we made oxygen. And if you start looking at the chemical reaction, can we figure out which one we made? Why does one side bubble more than the other? You know, if you look at the chemical equation, can you figure out which one is the one that's bubbling more? So, so you can try that out at home. Make sure you don't hold on to the wires too long because they get hot. Conducting electricity, it gets a little warm. But then now we're going to take a look at the actual chemical reaction. Okay, so we come back. We have water right here. And we saw the water in the cup, and it's, even though we have stuff dissolved in it, it's still water. And then we are going to put electricity in it, and we're going to split it apart and make hydrogen gas. So it's not just H by itself, it's actually H2. So hydrogen gas is actually H2. So we have the stuff breaking apart and reshuffling and forming H2. And we also have oxygen, O2, forming, break it apart, reshuffling, forming O2. What does that look like when, you know, can I have one of each, or does it have to have different numbers of each? Why does that have to have different numbers to allow for the mass, the conservation of mass to stay the same? All right. Good luck.